Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Milky Way's core, Planet 9, and first molecule. Magnetic map reveals secrets of Milky Way's core. At the very center of our Milky Way galaxy is a wild and mysterious area full of swirling gas, stars being born, and strong forces we can't normally see. Scientists have just created the first detailed map of the magnetic fields in this chaotic region, giving us new clues about how stars are formed and how they grow in such intense conditions. This research was led by a PhD student named Roy Zhao from the University of Chicago. He and his team focused on a part of space near the galaxy's core known as Sagittarius C. This area is packed with dense gas clouds and powerful forces, and it plays a key role in helping scientists understand how everything in the middle of the galaxy fits together. Think of it as a cosmic decoder, like a Rosetta Stone, helping us understand complex galactic behavior. To look into this mysterious place, the scientists used a special telescope called SOFIA, which was mounted on an airplane and could study light in the infrared range before it was retired. This kind of light is created by tiny particles of dust floating through space. These dust grains are very small, but they act like tiny compass needles. They line up with invisible magnetic field lines, and the light they give off tells scientists how those fields are shaped and where they go. What they found was fascinating. The magnetic fields are wrapped around a giant bubble of hot gas. This bubble was pushed outward by strong winds coming from a group of massive young stars. These stars blow out so much energy that they create a sort of shell of gas and magnetic field. This explains something that has puzzled scientists for a long time: strange narrow streams of fast-moving electrons that shoot across space near the center of the galaxy. These fast electron streams were first seen back in the 1980s by the same professor who now advises Roy Zhao. For years, no one was sure where they came from. But with these new magnetic field maps, scientists now have evidence that these streams are created when magnetic field lines snap and reconnect with each other. This action launches particles to almost the speed of light. The research gives us a clearer picture of how everything in this part of the galaxy works together. Cold gas where stars are born, hot regions filled with ionized particles, and the strong magnetic fields are all linked. They interact in a kind of cosmic dance that controls how matter behaves and changes over time in the center of the Milky Way. One of the most surprising things was how well this study matched with earlier studies using different tools. For example, the edges of the magnetic fields matched perfectly with the locations where scientists had found glowing carbon in another survey. They also found that a very powerful and rare kind of star, called a Wolf-Rayet star, was sitting right in the middle of this expanding bubble. This kind of research doesn't just help us understand our own galaxy. It helps scientists understand how galaxies everywhere in the universe form stars and organize their matter. By studying this one extreme part of the Milky Way, we're learning about the rules of the universe itself, how stars are born, how they grow in wild places, and how invisible forces like magnetic fields shape everything we see. The hunt for Planet 9. Some scientists think there might be a large, hidden planet far out beyond Neptune in our solar system. This idea isn't new. People were already wondering about it before Pluto was even discovered in the 1930s. Back then, astronomers noticed that Uranus wasn't orbiting exactly the way it should, based on what the laws of physics predict. They thought maybe an unknown planet, much bigger than Earth, was pulling on Uranus with its gravity and messing up its path. Later on, scientists figured out that this strange orbit was actually due to an error in calculating Neptune's mass, and the mystery seemed solved. But in 2016, two scientists at Caltech, Konstantin Batygin and Mike Brown, came up with a new idea. They believed there might still be another large planet, what they called Planet 9, based on how objects in the Kuiper Belt move. The Kuiper Belt is a huge area beyond Neptune filled with small icy worlds, asteroids, and dwarf planets, including Pluto. These objects in the Kuiper Belt don't orbit the Sun in neat, expected paths. Instead, many of them seem to follow odd, stretched-out paths that suggest something big is tugging on them. Badigian and Brown suggested that this something might be a large, hidden planet far beyond Neptune. They compared it to the way the Moon moves. The Moon orbits Earth, and together they both orbit the Sun. From far away, the Moon's path looks like a spiral because it's being pulled by both Earth and the Sun. Similarly, objects in the Kuiper Belt might be getting pulled not just by the Sun, but also by this mysterious Planet 9. At first, not everyone agreed with this theory. But over time, scientists started noticing more strange movements in these distant objects, and those observations seemed to support the idea of a hidden planet. In 2024, Brown even said he believed Planet 9 almost certainly exists because nothing else fully explains what scientists are seeing. In 2018, a new object called 2017 of 201 was found. It's a small world, about 700 kilometers wide, with a very stretched out orbit around the Sun. Its weird path might have been caused by a collision or by the pull of Planet 9. Still, there are problems with the theory. If Planet 9 is real, why haven't we seen it yet? Some scientists think we just don't have enough data to say for sure. Others suggest different causes for the strange orbits, like a ring of space debris or even a small black hole. One of the biggest challenges is that these objects take a really long time to orbit the Sun. For example, 2017 of 201 takes about 24,000 years to complete one orbit. That means we haven't been watching them long enough to clearly see the effects of another planet's gravity. New discoveries have made things even more complicated. In 2023, astronomers found another distant object called 2023 KQ-14. It's what scientists call a sednoid, which means it spends most of its time far away from the Sun, in a zone where the Sun still has some gravitational influence. It doesn't seem to be affected much by Neptune, and its orbit is more stable than some others. The fact that we've now found 4 of these sednoids, all with fairly stable orbits, raises questions. If Planet 9 is really out there pulling on things, we'd expect more chaotic movement. So if it exists, it must be much farther away than we thought, maybe over 500 times farther from the Sun than Earth is. Finding Planet 9 is extremely hard. Even our fastest spacecraft would take over 100 years to reach the area where it might be. For now, we have to rely on powerful telescopes on Earth and in space to keep searching. As we build better instruments and find more distant objects, we might eventually discover something that confirms, or disproves, the idea of Planet 9. So the mystery continues, and it could still take years to solve. How the first molecule helped stars form. Right after the Big Bang, which happened about 13.8 billion years ago, the universe was incredibly hot and dense. But in just a few seconds, it started cooling down. This cooling allowed the very first elements to form, mostly hydrogen and helium. At first, these elements were in a charged state and couldn't form complete atoms. It took around 380,000 years for the universe to cool enough for atoms to form when electrons joined with these nuclei. This change made the universe more stable and ready for the first chemical reactions to happen. The first molecule ever formed in the universe was called helium hydride, written as helium hydride ion. It formed when a helium atom combined with a positively charged hydrogen nucleus. This molecule played a key role in starting the chain of events that led to the creation of molecular hydrogen, or H2, which is the most common molecule in the universe today. After atoms formed, the universe went through what scientists call the Dark Age. During this time, there were no stars or other light sources yet, so even though space had become clear, it was still dark. It took several 100 million years for the first stars to appear. Even though there was no light yet, molecules like helium hydride ion and H2 were important during this time. For stars to form, clouds of gas had to shrink and get hot enough for nuclear reactions to start. But this only happens if the gas can lose some of its heat. This heat is lost when atoms and molecules bump into each other and release energy in the form of light. When the temperature drops below about 10,000 degrees Celsius, hydrogen atoms don't release much energy this way anymore. Molecules like helium hydride ion become especially helpful because they can still give off energy by spinning and vibrating. Because of this, scientists think helium hydride ion helped early gas clouds cool down enough to form stars. The amount of this molecule in the early universe may have made a big difference in how easily stars could form. Helium hydride ion often broke apart when it hit hydrogen atoms. This created neutral helium atoms in another molecule, molecular hydrogen ion, which then reacted again to form normal hydrogen molecules. All this helped lead to more H2, which also helped with cooling and star formation. Scientists in Germany at the Max Planck Institute for Nuclear Physics managed to recreate one of these early reactions. Instead of using normal hydrogen, they used a special kind called deuterium, which is hydrogen with an extra particle in its nucleus. When helium hydride ion reacts with deuterium, it makes a different molecule called HD and a neutral helium atom. This experiment was done in a special machine called the cryogenic storage ring, which can simulate the cold and empty conditions of space. The ring is about 35 meters wide and can hold ion particles for up to 60 seconds at very low temperatures, close to absolute zero. The scientists shot beams of helium hydride ion and deuterium at each other and measured how often they reacted. They discovered that, unlike what earlier theories predicted, the reaction didn't slow down at lower temperatures, it stayed steady. This means the reaction between helium hydride ion and hydrogen or deuterium was likely much more important in the early universe than scientists had thought. This result also matches newer calculations by other scientists, who found mistakes in earlier models used to predict this reaction. The updated models now agree with what the experiment showed. Since molecules like helium hydride ion and hydrogen were so important in helping the first stars form, this new discovery gives us better insight into how the very first stars may have been born.